Okay, everybody, we're on Module 14, so that's Labs 28 and 29, I think. So you'll have open to the correct page in your book there. Okay. Here we go. We're going to be taking what we know now about our criteria that it takes for a chemical reaction to proceed. So remember, it has to meet certain thermodynamic criteria. They have to be met, and once they're met, will all reactions proceed? And if they do have a good delta H, then yes, they will. Okay, if their enthalpy is good, then we can proceed. But sometimes the rate will be very, very slow. So y'all are writing this down, I believe. Yes, reaction rate is the rate of change of a product in a chemical reaction. So keep in mind what we're doing here. We're starting with a reactant and we're ending up with products. So if this reaction goes the way it shows here on the screen, I'm going to end up with less and less of this on the left, yes, and more of these on the right. Makes sense, right? So I'll be depleting, and the concentration will be lowering here, and the concentration of these will be rising up. Okay, that's what's going on in the chemical equation. But in this particular case, what we're looking at is we have H2O2. Remember what that is? That's called hydrogen peroxide. All right, we buy that in the grocery store, all right? I don't know if you've ever noticed, but the bottle that you buy that in is a opaque brown bottle, all right? And that's because this reaction is taking place spontaneously, where H2O2 is breaking down into H2O and oxygen, all right? So the oxygen will be in the form of a gas. It'll be releasing from there. And then, so if I have H2O2 sitting around for too long, guess what at the end all I'm going to have in that bottle? I'm just going to have water in there. Yeah. Here's the deal, though. It's really, really slow. Really slow. It's so slow. And in fact, it's even slower if it's kept in a dark container. And that's why they do that. If it gets exposed to light or heat, that actually will increase the rate of that reaction. So that's what we're talking about this week, is reaction rates. How fast does it go? How quickly can we get a reaction to take place? If I need it to go faster, what can I do to make it go faster? You might already know that. What do we do to it? We add something called a catalyst. So we're learning about catalysts today. All right, so since this goes very, very slow, typically the bottle that you buy at the grocery store will actually be hydrogen peroxide. The vast majority of it. There may be a little bit of water and oxygen. If the bottle's kind of bloated because it had a lid on it, that means some oxygen's definitely been produced there. Okay? So typically you won't see that. If I poured you a beaker full of H2O2 and you looked at it and I'd say, watch for those air bubbles coming out. No, you'd be staring at it for a long time, okay? Because it's that slow. Okay, so what needs to happen for that do we have to have that thermodynamic criteria met? And then the reactants have to be close enough together. We have to put them together. All right, that's known as the collision theory. We have to be where their valence electrons are touching each other, and therefore they can react with each other. That makes sense, right? So we meet the thermodynamic criteria, and we get a nice fast reaction, and we'll have our products made in a timely fashion. All right, this one, what are we looking at here? We have CH4, that's methane, and we have oxygen all around it, and we're going to end up with CO2 and H2O. What kind of reaction is that? It always ends up with CO2 and H2O at the end. Combustion. It's a combustion reaction. So as long as I have O2, it's okay, right? But typically in something like this, the thermodynamic criteria are met, and in order for it to proceed, it needs a pretty high activation energy. All right, in this particular case, a spark, right? A flame, something to get that activation energy going, and then boom, it'll go on this. In fact, this could be quite explosive, and so we'd have trouble. One of these might be exploding. All right, so this is just showing you that collision theory. We have these little molecules getting close enough to each other. They're moving around, they're all moving, and therefore if I am dealing with two solids, they're not moving very much, right? I got to put those solids, stir them together, maybe something like that. I might manipulate the experiment, maybe I could heat them up. What does heating up do to my molecules? Speeds them up. It speeds them up. If they're sped up, is there a better chance of colliding with another molecule? Absolutely. So that's all that's going on in chemistry, y'all. It's that simple. All right, so this is called reaction kinetics. The word kinetics means to move around. Okay, so we're having kinetic energy right here. Remember last time we talked about how we had potential energy in the bonds, and then we go through the reaction and they break the bonds? So those breaking of the bonds, that's kinetics. And we're going to rearrange everything. So here's that same definition, the rate of change of a product into a chemical reaction or change in the concentration. I put the word concentration in those brackets so you'll remember those brackets mean concentration. So when we see that in an upcoming equations here, you're going to know that that means concentration. All right, so this is going to tell us how fast a reaction will proceed. Remember, those valence electrons need to get close to each other. That is collision theory right there. All right, so this is your first formula. It's 14.1. You're going to write this in that first box, I believe. Is that right? So R, meaning the rate, equals the change in the concentration of the product. That's the product. Notice those brackets around it. Over the change in time equals negative the change in the concentration of the reactants over time. Change in time. Now, the reason it's negative is because the reactants are disappearing. Right? The concentration is getting lower. All right, interestingly, we won't really use this formula very much. You need to know it. But we're going to use something else that makes it a little more, this is what we'll use in an experimental sense. And when I say we, I'm not talking about us, because the experiments to do these processes are way too complex for a high school chemistry class. Just for we don't have the equipment. Okay, so it means that the rate can be determined by experimentation, measuring the change in concentration of one or more of the reactants. Remember, I just wanted to put this down, M equals number of moles over liters. That's molarity, because we have our unit's going to be molarity per second. So M is molarity this week, okay? All right, factors that affect the reaction rates. These are, you're going to write in those boxes right there. First of all, in order to react, the chemicals have to come in contact to each other. Okay, so that means how close are they? They need to be close together. Close enough, right? Write down, they need to be close enough to each other. Here we go. Higher temperatures increase reaction rates. That makes sense. Concentration affects rates. Usually, if I have a higher concentration, I have a faster rate. Increased surface area will increase the rate, and adding a catalyst. Oops, I made you have an extra box, didn't I? Sorry. Adding a catalyst will help increase the rate. Okay, so we'll be talking about each one of these things and actually trying to measure that concentration as we go. All right, so the math that we'll be doing this week is not difficult. Just takes you remembering what to do when. Good morning. Okay, so was there only 4 blanks in there? Sorry that I made you put collision at the top. They have to touch. All right, here we go. But it's important to know because it's always it is the way to control chemical reactions. Okay, we can manipulate a chemical reaction by doing one of those things, by increasing the temperature, by increasing the concentration, by increasing the surface area. You'll need to remember all this for next week's lab, okay? And by adding a catalyst. We'll be adding a catalyst and looking at the difference between concentrations next week. It should be fun. Okay, so we're going to control our reactions. Let's watch a little video about it.
Chemical reactions happen faster at higher temperatures because the individual molecules are going faster and therefore causing more collisions. For this experiment, you're going to need 2 glasses of the water. The glass of water on your left is hot water. I heated it in the microwave for a minute. The glass on your right is cold water, just ice water. You'll also need 2 effervescent tablets. We're going to drop the tablets in the glasses. Which do you think is going to react faster? The one on your left, which is hot, or the one on your right, which is cold?
Guess it's hot. Oh, wow.
As you can see, the one on the left is reacting much faster. It's the hot water. It's almost done dissolving at this point. The one on the right is cold water. You can see down at the bottom of the glass, the tablet is still dissolving.
All right, you get it. Also, decreasing concentration decreases the rate because there are fewer reactant molecules to hit each other. Totally makes sense, right? So if there's fewer, there's less stuff. So we can talk about bringing in our concentrations there, or upping our concentrations. What about our surface area? This exposes the amount of area that can be subject to the reaction. So we're looking at some chunks of wood right here, and they have a little surface area compared to chips of wood. So which one is easier to combust? The chips of wood. In fact, I will tell you there have been incidences of the wood chips like this spontaneously combusting. That can happen, and it has to do with their very small particles. In fact, many times very small particles, because of that increased surface area, can be subject to combustion. Even things like the dust off of corn and wheat and stuff like that actually can combust spontaneously because there's oxygen all around, yeah, and so sometimes it will also lower that activation energy, that activation energy, yeah. Okay. Let's look at, now this is great. This is going to show you, we're not going to do this in class, so I'm showing you a video of it. This will increase the surface area of ethanol. Oh, I don't think there's any, no there is, she's talking on it in just a second. I think she's a British lady. It's highly flammable, that's why we're not using it.
Alright, the demonstration we're going to do today is to show the combustion of ethanol, a highly flammable liquid. Okay, so we're going to take our ethanol, we're going to pour all our ethanol into this large bottle here, and then we're going to shake the bottle around. What we're doing here is we're making ethanol vapour. With a really good shake. Alright, and there should be now very, very little left in. So, now, at arm's length, using a taper, I'm going to light the taper and light the vapour inside the bottle.
So you see that increased surface area there. much more combustible. That's why we're not doing it. And that's the reaction that took place right there, combustion. All right, so this is going to be the big star of the show today. This is the one you're going to need to do your, write that down, of course, and then you're going to be doing some math problems based on the rate equation. Okay, so let's look at a reaction. Okay, you're going to, do you have a place to write this part down? How much room do you have for rate equation? This isn't actually the rate equation just yet. Okay, so don't put this down just yet. Let me just tell you what's going on. All right, so I have a reaction. I have a reactant A being added to reactant B, and I'm making product C and product D. Right? That's what's happening here. The little a, the lowercase a, and the lowercase b, c, d, those are the stoichiometric coefficients. All right, so just whatever is in front of them, 1, 2, 3, 4, 5, whatever it is. All right, there is the, that's the rate equation right there. So R, the rate, equals little k. K stands for the rate constant, multiplied by the concentration of A to the x power. That's going to be its rate position, and the times concentration of B to the y power. Now, sometimes we'll watch a video in a minute that uses different letters, numbers, whatever for those x and y. We're using x and y. That's arbitrary. But that is the actual equation that we'll be using to do our math deals, and we have to figure things out. We're looking for R for the rate, okay? But we will not know K, we will not know X, and we will not know Y. Oh my, 3 unknowns, how fun. All right, so what we have to do is we really have to go through, do an experiment to compare some rates and things like this to find those. We'll be able, because of experiments, be able to find X and Y. Once we find X and Y, that will give us the R in the sense that the R is the rate taken during an experiment. So we'll have R, X, and Y, and then we'll be able to figure out K. All right? So X is the order of reaction with respect to A. Y is the order of reaction with respect to B. All right, and K is the rate constant. It's not constant like the speed of light is constant. It's constant for a particular reaction at a particular temperature. All right, so It's kind of weird to call it a constant. It's constant for that. So that's why we don't know that from a chart somewhere. It really depends on how the experiment went. So we do have to get our data from an experiment in order to solve these equations. Now here's the deal. We can't do the experiments. We don't have the equipment to do the experiments. So therefore, we'll be doing other experiments that don't require a bunch of math. Yay, right? Labs should be fun, not full of math. Okay. Now, but for your quiz and for your study guide this week, you'll be doing based on some lab data that's given to you, all right, which we'll show you in just a minute. So there it is, R equals K, A to the X, B to the Y. It's restating what each one of these are, rate constant. It's unique for each reaction. It has to be determined through experimental data. We're going to find those X and Y's, which are the rate orders calculated by experimentation. That's just a little review of what I just said. All right, so let's try our first one right here. Write the rate equation. Look what it's asking for. It's just asking for the rate equation. That's all it's asking for, okay? So it says here we have N2 plus H2 gives me NH3. It looks like it's balanced there. I will tell you what you need to understand, and it's going to seem a little weird. Our stoichiometric coefficients do not help us this week. They do not help us. But there's so many times you're going to end up with that being the same number as your rate in the X and the Y, the exponents. But don't buy, it's coincidental. It just happens to happen a lot, apparently. Okay, so here's my rate equation. My rate equation is R equals K times N2 to the X and H2 to the Y. All right? That's all, that's the whole answer to that one. There's no way you can proceed with understanding any more of these unknowns unless I give you data. And in this particular case, I'm not giving you any data. Therefore, this is the answer. That's your rate equation for this reaction. Notice I don't do anything at all with our products. I'm just using the reactants here because that's what we're changing that concentration of those, right? We're seeing, remember the rate's telling us how fast is it going. So we're literally measuring time here. Okay, so finding rates using experiments. It requires fancy equipment, so we use data to calculate instead of experiments. So if the reaction is unaffected by the concentration of one of the reactants, the exponent rate of the equation, that little x or y, is 0. So this doesn't make any sense to you right now, but it will in a minute, okay? If the reaction rate doubles, we're talking about time here, the exponent will be 1. Okay, so if I double my concentration and my rate doubles, that's a 1-to-1, my exponent is 1. If it goes up by a factor of 4, the exponent is 2. I know this sounds confusing right now, okay, but when we do it a couple times, you'll see what in the world I'm talking about, okay? I just think, were these blanks to fill in or something? Right there? No? Okay. All right, we just have to remember that. Double equals 1, 2 equals 4, 4 equals 2. All right, now this is Professor Dave, and he's going to explain this to us, all right? He uses different exponents besides x and y, so don't pay attention to that. And when he gets to the end, he gets real complicated, and we'll just move on when he gets to that part. All right, let's listen.
Study of reaction rates, or how fast a reaction goes. There are a lot of reasons why one chemical reaction might happen in the snap of a finger, and another might take a whole day. So let's learn about what those reasons might be. Reaction rates are generally measured as an increase in the concentration of products per unit time, or molarity per second. So, for the following reaction, we can discuss the rate as the change in the concentration of each product over the change in time, or the change in concentration of reactant over change in time, though that one will be negative since we are using up the reactant to make products. Remember, the triangle is a capital delta, and it means change in, and brackets mean concentration. Rates of change will obey stoichiometry, so for example, if we look at this reaction, we have to understand that oxygen appears at 1/4 the rate of NO2, and at 1/2 the rate at which N2O5 disappears. We can measure rates of reaction in different ways, but any method will involve measuring the changing concentration of a substance. For example, if the product of a reaction is a gas, we can measure the changing pressure of the gas being produced. If a reaction goes from clear to a colored solution, we can monitor the light absorbance using a spectrophotometer. But whatever we do, we can use the data to plot concentration versus time. When looking at this data, we can calculate the instantaneous rate, which is the rate at any given moment. We do this by looking at the slope of the tangent line at a point, or the line that just touches an individual point on the line. This is more precise than taking an average value over a range of points. The rate will always depend on the concentration of one or more reactants in some way. The relationship between the rate and a particular concentration is illustrated by the reaction order with respect to a particular substance. For example, let's say we run a reaction several times with different initial concentrations to see what it does to the rate. If we keep everything else the same, but we double the concentration of one reactant, and as a result, the rate doubles, then the reaction is first order with respect to that reactant. Instead, if we double the concentration and the rate quadruples, the reaction is second order with respect to the reactant. And if a change doesn't affect the rate, it's zero order. The overall reaction order is just the sum of the orders from the individual reactants. So, if a reaction is first order with respect to each of two reactants, it would be second order overall. We can describe the
Okay, so he gets a little more detail. We don't need that detail. All right, so do you see what he's doing there? We're going to take data. That's what he was doing. He was taking data based on different trials that we run on a certain reaction. So we're going to have a reaction at one concentration and a reaction at a different concentration, and we're going to see the difference. And that difference will tell us something. So we will be able to intuit then, mathematically actually, through the equation what the rate orders are. So to determine the exponent associated with the reactant's concentration, all we have to do is hold everything else constant and see what happens to the rate when the concentration of only one of the reactants changes. And that will tell us what the exponent must be. All right, so let's do an example. I think it's the only way to really understand it. Here we're looking at an experiment. A chemist runs an experiment designed to determine the rate equation for the following reaction. 2ICl plus H2 yields I2 plus 2HCl. Okay, so what we're going to do is here's our concentration of ICl, our initial concentration of ICl. In trial 1, it's going to be 0.25 m. In trial 2, we're not going to change it at all. It's 0.25 m. And then in 3, we doubled it. Okay, so now what we want to see is what's happening over here. We have 0.25 for H2 over here, and then we have 0.5 and 0.5. So notice here, if I have both of them at 0.25 molarity, I'm going to end up with an instantaneous reaction rate, we just call that R, our R right there, at 0.0102. So we're now going to base everything off that number. All right, so now what I'm going to do is I'm going to take ICl, when it goes, it stays the same. But now I'm going to look at when I double H2. So when ICl stays the same, H2 doubles, what happens to my rate? Does it double? Okay, right, it doubles right there. So since it doubles, we know then that that is going to be 1. Right? Because it doubles and it doubles. That's 1-to-1 ratio. Does that make sense to you? So that since it doubled, remember that rule? Since it doubled, our exponent's going to equal 1. Has everybody got it? You understand? Okay. So that's going to be our up here. It's going to be a 1. And now we're going to look at the next one where we see this stays the same, but we change the ICl. Okay, so here's the ICl. This is the same, 0.5, 0.5 for the H2. And then when it changes, what happens between here and here? Between 0.0204 and 0.0408, that doubles. All right, so what does that tell me with respect to H2, comparing these two, what is my rate order? Since it doubles, it's 1 again. Do you get it? So therefore, when I look at it, I'm going to have my R equals K, ICl to the something, H2 to the something, and we know those are 1 now because of the data we looked at. How do we feel? Do you get it? Is it clicking in your brain? We'll do lots more, okay? Because here's what the deal is on this one. Practice makes perfect. Okay, we're going to practice these. Practice. Okay. All right, so that's what we're going to do. We're going to have a, in fact, you know, on your quiz you'll have a chart similar to that with data on it. Okay? And typically it'll be 3 trials because that makes sense. You know, unless I have more than 2 reactants, right? If I have 3 reactants, things get yikes. I got to go and really, you know, make a big chart for that one. I think we probably won't have one like that. That page number now is correct. I had the wrong page number before. Page 500 is correct. That's where we are in our book. Okay? All right, so now we want to take what we know and solve for K. All right, we know that R equals K, ICl to the 1, H2 to the 1. Now let's solve for K. So how do we do that? Well, we know R. All we have to do now, y'all, all we have to do is pick one trial, one of them. It doesn't matter which one. Just pick one of them all the way through. And I just happened to pick trial number 1. And in trial number 1, we know that our instantaneous rate right here is 0.0102. And we can put that in for R. Do you see what I did? Here's R, came from right there. See it? Came from the chart. Equals this to the first, which came from the chart, 0.25. And we know we don't have anything up there. It's just a 1 and a 0.25 right there. I do the algebra right there, and I end up with 0.161 over molar second. That's the unit right there. That's a 1 over molar second, which is a little clunky. So now we can say R equals, we can plug it all back into this, R equals 0.161 over molar second, concentration ICl, concentration H2. That, on the bottom, the R equal, is my final answer for this. Because we were looking for that, okay? There's no way we could have got to here without doing the stuff we did on the previous slide, finding our X and our Y. Okay, so does that make sense? You get it? It's not difficult, and that's why if you just practice a few of them, you're like, oh yeah, I got this. Not hard. A little bit of algebra right there. Okay, so we got to remember to solve for K. I think on this one originally I hadn't solved for K, and I had to go back yesterday and do that. All right, page 502, here we go. A chemist runs an experiment designed to determine the rate equation for the following reaction. 2NO plus Cl2 gives me 2NoCl. Looks balanced right here. It's going to run this reaction. There it is. And here we have our trials. Okay, so for instance, NO is 0.50, and then 1, then 1. Initial concentration of Cl is going to be 0.50, 0.50, and 1. And you can see our rates over here. So let's look at our first one here. When they're both the same, 0.50 molar NO and 0.50 initial chlorine, we're going to end up with an instantaneous rate of 0.019. And then when we take our concentration here, this stays the same for Cl, but it doubles for NO. What does it do to our rate right there? Who's got that in their head? 0.019. Is it quadruple? It's 4. Okay. So what do we know then about that? Exponent's going to, if it's 4, then the exponent's going to be 2. Thank you, 2. All right, then we're going to go down here where this one stays the same, and this one changes from here, 0.076 to 0.152. What's that one? Is that just 2? Is that doubled? Okay, y'all have that in your brains? Okay. All right, so then we're gonna be looking at a 2. So we have our X and our Y right here. So which one's going to be X and which one's going to be Y? Let's go. Make sure we do it right. Oh, here it is. Oh, all right. I'm going to go through it sentence by sentence. Good. That'll help me. All right. We're going to find X first. We're going to use trials 1 and 2. That's the only problem right now. We can't actually look at the data chart because it's on the last slide. I don't have room for it on here, right? Okay. We're going to use trials 1 and 2. The concentration of NO changed, but the concentration of Cl did not. NO doubled. The rate quadrupled, so it equals 4. So 2 to the X equals 4, so X equals 2. So that's X equals 2. Finding Y, we're going to use trials 2 and 3. Concentration of Cl changed, NO did not. The Cl2 doubled, the rate doubled, therefore our Y is going to equal to 1. Do we all understand that? We all see how we got that? Okay. So now we're going to put it into our equation like this. See where our 2 went, and our 1 is right there. All right, so to determine K, we're going to choose one of the trials. We're going to plug in the numbers. And after I remember, one of the trials didn't have a bunch of 1s in it. I love 1s with math, right? I love 1s. Okay. So I think, yeah, there it is right there. So 0.152, which came from the chart, gave me a K with the 1 to the second power times 1. Yay. Love all those 1s. And then I'm going to do that math real quick, divide that, and end up with my K equaling here, 0.15, 1 over molar squared seconds. Notice how that unit is different. So those units will change depending on what you're doing. And so just make sure and cancel out as much as you can. So we should have canceled some stuff out there. So R equals 0.15 m2 over second. It seems like it should be over that. And NO2Cl with the 1. All right, yeah, I think my unit's a little messed up there, y'all. Sorry about that. But that's my answer, what R equals. And so I had to have that chart in front of me at all times. And you will have that on your quiz. You will have that in your problems you work on in your study guide, okay? You'll be looking at the chart the whole time. Okay. I can't remember which one that was. 14 point something. 14.3. Okay. All right. 14.3 part 2. In order to determine the rate equation for the following equations, this one right here, a chemist performs a rate study and gets this chart. All right, so let's see what happens. This is going to be an interesting one here. Look at these closely. Here it's the same in trial 1 and 3. And it changes concentration in 2. And then this one's the same in 1 and 2 and changes concentration in 3. And so we're going to go through this, kind of look at that in your minds, check this out, check out the rates, what's happening here. And look at this last rate. There's no change. There's no change when what happens? When the OH, when the hydroxide is doubled, the rate doesn't change at all. So what does that tell us about the hydroxide? It's not affecting. It's not affecting the rate. The concentration of OH is not affecting the rate. So if we want to increase the rate, we're not going to change our concentration of hydroxide. That wouldn't make any sense. We have to change our concentration of whatever that thing is. All right, let's go through it step by step. Here we go. We're going to be looking for our rate here, and so you see where we got this, right? Here's our reactant with our X's and our Y's. We're going for X. For X, we're going to use trials 1 and 2, where the concentration of the carbon molecule doubled, the reaction reagent doubled, so the X equals 1. To find Y, we use trials 1 and 3 because the concentration of OH doubled and the reaction rate stayed the same, so Y equals 0. If it's not affected, it equals 0. So we're going to put that in. What happens when you have something raised to the 0 power? It turns it to 1. It's just 1. So we can just get rid of it. Which makes sense if I'm looking for a rate and OH doesn't change the rate. What does it even belong in there for? Leave it out. Get rid of it. So there it is. Here's what we have. We have R equals K and only the concentration of our carbon molecule. So then we can go solve for K. By using the data, I used trial number 1, which was this, 0.0010 meters per second equals K times just the concentration of the carbon molecule. And so then we do the math right there, and we end up with 0.0101 over second. Interesting. Our molar all canceled out there. And so our R is going to equal 0.0101 over second concentration of the carbon molecule. That's our final answer. Doesn't this seem like a philosophy class or something? It's like, what am I actually ending up with? But this is the way we do things like explode that gas in that giant bottle here. If you want to miss this. Okay, important to remember, sometimes the rate of a chemical reaction will be unaffected by a concentration of one of its reactants. In this case, the exponent is 0 for that reactant. We can drop that term from the final equation because it has no influence on the rate. No influence on R. All right, which is what we just covered in that thing. All right, so now the rate orders. So those little X and Y that we found, we're going to now call those the order, and then we're looking at those are the rate orders, and now we're going to find the overall order of the entire equation. So the rate order of the equation, this is the most fun right here because guess what? All we have to do is add. All we have to do is add. All right? So I have this underlined. The rate order of a reaction is the sum of the exponents. The sum of the exponents. The reaction rate orders for a chemical reaction are determined, this is underlined, experimentally, and they are not based on the stoichiometric coefficients of the equation. I believe those are blanks at the bottom, yes? So fill those in. So we can, in fact, I don't think we do any stoichiometry at all in this module. Yay! Hallelujah. All right, let's watch a, this is just real quick right here to show us how to find that overall order of a reaction.
Okay, distinguish between these different terms. So here's a generic rate equation. Square brackets means the concentration in molar, and A, B, and C are reactants in whatever equation we're looking at.
Those were apparently
So
calculated.
K is the so-called rate constant. You can only change that by changing the temperature or adding a catalyst, which DIB doesn't really need you to know. And the rate constant is specific to each different reaction. It's not like pi that's constant for everything, it's different for each reaction. And the order of reaction is the superscript. So for A, the order of reaction with respect to A is 0. For B, the order of reaction is 1, and obviously for C, the order of reaction is 2. Now these aren't necessarily the coefficients in the equation. It's not like the equilibrium constant where the coefficients in the equation go there. You have to do an experiment to work out those little numbers. The overall order of reaction, well, that's just add up the exponents in the rate equation. So 0 plus 1 plus 2, sum means add, gives me 3.
And that's it. That's how you find the overall rate equation. Pretty cool, right? All right, so check this one out. A chemist does a rate analysis of the following reaction. We have hydrochloric acid and sodium hydroxide making H2O and NaCl. That's an acid-base reaction. You should recognize that because we have water and salt formed. The experiment reveals that this reaction is first order with respect to each of its reactants. What is the rate equation? That's the first question. What is the rate equation? And what is the overall order of the reaction? Okay, so it's not asking me to do, it's telling me what we already got experimentally. We have our rate orders already. All right, so we know that our R is going to equal K with our HCl or NaOH. That's just this with no superscripts, right? Because we know they're ones. So what's the overall? 1 plus 1 equals 2. Voila. Yeah, y'all will hope for questions like that on your quiz, yeah? That's nice. You do have to write out the rate equation because it asks for it. Notice I can't get K here because I don't have any more data from a chart that told me what a rate at a particular spot in the reaction, what it was. So I can't solve for K here, but I can tell you the overall rate of the reaction, which is 2. This is one of those places where I'm like, okay, and what? I don't know. But we can answer these questions, right? It does tell us, of course, that the concentrations of each of those do affect the rate. We can mess with the concentration of them, and they will affect the rate in some way. We don't know right now because we don't have that chart. All right, practice determining rate orders. I don't know if that page number is right, but this is apparently OIO 14.5 maybe. Might be from the old book. All right, 2PO plus BR2 equals 2POBR. It is determined by experiment to be second order with respect to PO and first order with respect to BR. What is the rate equation and the overall order of the reaction? All right, so here we have R equals KPO with a 2 right there because it told us it was second order, and BR is first, so there's a 1 up there. Overall rate 2 plus 1 equals 3. All right, so that really gave us all the information we needed right there in our question, and we can answer that quickly. No worries. And of course, if there are blanks that we didn't fill in some of the OIOs, that's because you're supposed to do those on your own, right? Okay. But some of them I did for practice. Here we go again. It is determined with this reaction right here to be first order with respect to our carbon molecule and 0 order with respect to our sodium molecule. What's the rate equation and what's the overall order of the reaction? So what can we do with our sodium? If it's 0 order?
Just leave it out.
We just lose it. We can just lose it. Right. So here we go. Oops, did y'all need that? Y'all need that equation? For those of y'all who are writing it down. Who's got, first of all, you can tell me the overall order, rate order. What's the overall rate order? 1. It's just 1. 1 plus 0 equals 1. Okay, and then what are we going to do with our rate equation? We're going to have our R equals K with only one bracket, yeah? Yeah? All right, so it's going to look like that. K with our carbon molecule right in there, and then our overall rate is 1. Easy breezy. Summary. This is at the bottom of your page there. If the reaction is unaffected by the concentration of one of the reactants, the exponent in the rate equation is 0. You're just going to put a 0 there or write the word 0. It's at the top of the next page. Is that where it is? There's just blanks to fill in. If the reaction rate doubles, the exponent will be 1. If the reaction rate increases by a factor of 4, the exponent is 2. The reaction orders for a chemical equation must be determined experimentally, and they are not equal to the stoichiometric coefficients. Okay, so this little summary right here, I could picture some quiz questions coming right out of there. Okay, yeah, just some. And those are going to be freebies for you. Okay, freebie questions instead of having to do some calculations. Right? I'd always like the quizzes to have at least some non-math problems for those math strugglers like me in the room. Yeah. Okay. We're in 14b now. So turn on over to 14b. We're going to see how we're going to use that rate equation, and then we're going to talk about the catalysts. So there's a little bit of review. It says, what is your rate equation? It's that. We know this already, yes? And then it asks this question, the reaction rate orders for a chemical reaction determined experimentally, which we just said. I realize that. It's just everybody else would have been a week later. Got to put that back in your brain. We're keeping our continuity, though. So just keep on going, trudging through, right? Okay. So Professor Dave used that word is instantaneous rate. Okay, so what that means is that what's the rate at any instant? This thing's moving, right? This reaction's going. Think about the volcano, right? The volcano, the vinegar and the baking soda. It's like really bubbling at first, and then it calms down. So at any point of time during that reaction, there is theoretically a rate for every single point on that line. So we're looking for a point on a curve. All right, so is that geometry? Is that calculus? Calculus nearly killed me. Okay, calculus is the area under a curve. I know that. Okay, so but we're looking for a point on a line. So you know you could have to go through, and maybe chemistry 2 does this, where you're going through plotting it on a graph and then taking that point on the line and putting that into your data chart. That's where they got the data for those charts, off of a graph of an actual reaction that went. So it's the rate that's calculated for a specific concentration at a specific time. At a specific time and a specific temperature and all that business, okay? Are the reactants ever completely used up in a reaction? The answer is no. And this is going to sound like, what have I been lying to you all year? Okay, it turns out that when we run a reaction, I'll show you a chart here in just a minute, or a graph, we never actually completely use up all of the reactants. We get close, all right? And then furthermore, it actually runs backwards a little bit. Yikes. Next question, how did temperature and catalysts affect the rate? And you're just going to write that they increase the rate. They increase the rate. Remember, sometimes the concentration doesn't, but the temperature, raising the temperature makes sense. We're adding energy. And then we're going to be looking specifically at catalysts and how the catalysts accomplish this. Okay, so let's say we ran a reaction and we were able to measure very, specifically the plot lines. I'm going to end up with a chart kind of like this. I start up here with a bunch of reactants, and I'm losing reactants, losing reactants all this time. Now at this point, you see, I never get all the way down to 0, so my chart never actually comes down to 0. And I'm going to try to find that one point right here. So yeah, I'm going to use my, what is that? It's not geometry, but it's, what am I looking for? Trigonometry, it's trig. Yeah, it's trig. We're using our right angle right there to figure that out. So yay. So good thing you're getting a chart with all the data already in it. Okay? But that instantaneous rate is anywhere I put a tangent line along that curve right there, I can retrieve a point. I can come up with our actual number that goes on our chart right here. So this is more general, where I'm starting with lots of products and I'm going down, down, down. This gets to the bottom. It shouldn't. Meanwhile, I start with 0 reactants. I get more and more and more reactants over time. All right, so this is just showing a time situation and how those are changing. So chemical reactions never actually finish. They just keep getting slower and slower until they proceed imperceptibly slowly. This means that for any chemical reaction, no matter how long we wait, there will always be some of the reactants left. So when we show a chemical equation going all the way through, we have a limiting reactant and all that kind of stuff going on that really, even though we balance our equations and we know what's happening, it's really theoretical that it does that, okay? That's why you should never, drink anything from chemistry class. Oh, I just neutralized this strong acid, now I can drink. No, don't do that. Don't drink acid. Unless it's a Dr. Pepper. You can drink that acid, right? Okay, temperature drives rate. Now this is important. This is a general rule of thumb for us, okay? It says here, for every 10 degrees C increase in temperature, the chemical reaction rate will double. Do you have a blank that you're just supposed to write double in? Mm-hmm. Okay, for every 10 degrees C decrease in temperature, the rate is divided by 2. For our purposes in Chemistry 1, this will hold, okay? It is a general rule, but the temperature must stay the same. Because temperature is actually in the rate equation. We never really saw it. It was a little bit invisible because the rate constant's not completely constant. It changes with temperature. The way you find that is this equation right here. This is called the Arrhenius equation. Check it out. What do you think? That's got a lot of superscripts up here. We've got our activation energy in there. We've got our gas constant. We've got our temperature. I just want you to see that's how temperature plays into what K is. Fortunately for us, we don't have to use this equation. Hallelujah. I'm thinking chemistry 2. I'm thinking. I don't know. Never taught chemistry 2. Never will. But just keep in mind, we're going to use this general rule of thumb about this. That's a whole lot easier to remember than all of that business right there. Okay, let's see. A chemist performs the following reaction at 25 degrees C. What's going to be our standard temperature, standard pressure, that kind of thing. All right, 2NO plus Cl2 is 2NoCl. I think we've seen this one, yes? What will be the instantaneous rate of the reaction at 25 C if he runs the reaction with both reactions at a concentration of 0.15 molar? All right, so we have some information here. All right, we're going to say the rate equation is, it's given to us. And we see we have second order for NO and first order for Cl. They didn't tell us that, did it? It must have just given us the rate equation right there. So we have all this information given to us now. So now what we can do is we can plug some things in. All right, the rate constant at 25 degrees C, I'm giving this to you. This is another known quantity. At 25 degrees C, the K for this reaction is 0.151 over molar squared seconds. Okay, so now I can plug these things in. So my R is going to equal this number times this number. Okay, so the first number there, 0.151 molar squared over seconds, came from right here. That was given to me. My second number said that both reactants had a concentration of 0.15 molar, so I put those in down here. And then I know from our rate equation that the first one is squared because of the rate order. I do that math, I come up with this number. All right, and then, okay, so that's what it is, right? That's our answer. What happens at 45 degrees? So that's at 25. So what's the difference between 45 and 25? 20. And what does your little rule of thumb tell you? 10 degrees what?
10 degree increase doubles.
Doubles, and I did it twice.
So
okay, so using the hint, 45C is 20C above 25, so the reaction rate would double twice. So I take my number that I calculated, this 0.00051, times 2 times 2, and I'll end up with 0.0020 meters per second at 45. Okay? So that's going to be faster. You can see how that temperature makes that difference right there. So this is just a problem taking you through that. Look how much information it gave you. I have arrows here. I plugged that in there. I plugged those in there. All right, so that shows you where all those numbers came from. I didn't just pull them out of a hat. They were given to me. And also the rate equation was given to me. That was important. I needed that little exponent up there, yeah? Okay, so you'll definitely have some practice problems like this, and perhaps even a quiz problem like this. That's a lot of words on there, though. I don't know. I don't have room on a quiz sheet for that. I can't remember if it's on the quiz. But you need to know it regardless, yeah? Okay, so now let's move on to catalysts. This is kind of the fun part of this module, where we're going to be looking at catalysts. they will increase the reaction rate by doing something important. What they do is they decrease the activation energy. Remember, it takes that flame to get a fire going, right? So if I can decrease that amount of energy to do that, that's known as a catalyst. They do not get ultimately used up in the equation. So a catalyst is used and recycled at the end, okay? So, or it's just still there. The catalyst doesn't get used. I need you to understand that. Did we already know that about catalysts? It increases the rate, and then it's still there at the end. I still have it. It's not part of the equation. That's a little simplified, but we'll get to that in just a second. There's two types. There's a homogeneous catalyst, a catalyst that is the same phase with at least one of the reactants. Notice homo means same. That'll help you remember that. Heterogeneous catalyst, a catalyst that is different in a different phase than the reactants are. And there's a famous one for that we'll look at. That's our catalytic converter in our car. Okay, so two different kinds of catalysts, and the way that they are used in the reaction is different. They use different, what we call mechanisms, in order to move through there and get this reaction to go. All right, remember what I'm trying to do is I'm trying to increase the rate. So let's go back to my H2O2, my hydrogen peroxide. Can I increase the rate of that reaction anyway and turn it into O2 and H2O? Do y'all know a trick to do that? Have you ever done it before? Some of you might earlier, and you didn't know you were doing that. Did you know if I add yeast to it? Did you know that? If you add yeast to H2O2, it'll make that reaction speed up really fast. And guess what the yeast will do? It'll all bubble up because that's what's going into it, O2. O2 is going into it because I'm going from H2O2 to H2O plus O2. So if we're on a desert island and we need water, and we have hydrogen peroxide and yeast, we can make water. I don't know if I'll have all those things. I think I'd rather just have water. Okay, you got those definitions written down for the homogeneous and heterogeneous catalysts. Everyone, yeah? We're good? Okay. So this is what's happening when here is on the left side, you'll see here that I have a reactant and I have a product. In order to get to my product, boy howdy, it's got to climb this large hill right here just to get enough activation. Think of that striking match there. A lot of energy in that striking match to get that fire going, right? Well, if I have a catalyst, look what I can do. I can lower that activation energy way down, and therefore you can see how that would definitely speed that up. It would make it easier and it would speed it up. And that's the job of a catalyst. That's how they're going to manage that. Okay, so our homogeneous catalyst, remember that's the same, so we have our reactants. This is kind of a simplistic way of showing it. I've got my, the yellow thing there is our catalyst, and they're going to come together. That catalyst is going to bring them together, a matchmaker, right? It's going to bring those guys together, and then I have my product, and my catalyst is there to do it again. It's recycled, it's not used. Okay, I should say that differently. It's not used up. It's used, obviously it did something, but it's not used up. All right, our heterogeneous catalyst is a little different right here. Let's think of this right here as gas molecules, and they're hitting a surface which is a solid. That's a different type of phase, right? And what's happening is that different type of phase thing is causing those to come together and make our product, and my surface, it remains. The most famous one of these, of course, would be our catalytic converter in our cars. Okay, so this is what a catalytic converter looks like. It's a heterogeneous catalyst. Because what's happening in our car, y'all, is we are burning fuel. And burning fuel creates, it's combustion. So what am I creating? CO2 and H2O. But what happens if I don't have quite enough oxygen? What happens to my reaction? It's not complete combustion. Instead of CO2, what's it producing? CO, which is carbon monoxide. Carbon monoxide is deadly to us, okay? And furthermore, there's the H2O is coming out too. We have other things that burn in our fuel that end up, just impurities, things like this, end up putting some nitrogen, maybe some sulfur or something in the air. So back when I was young, the government decided that we wanted to have cleaner emissions coming out of our car, and we wanted to lower the amount of carbon monoxide that was coming out of there, okay? Because if you know, just recently, in fact, even with our catalytic converters, we still have carbon monoxide coming out of there. I don't know if you heard some people during the cold snap were so cold they went into their garage and turned their car on and put their heater on. Well, they didn't open their garage door. So what was building up in the garage? Carbon monoxide. I know at least one death that took place. Somebody in their car. You know, don't ever have a combustion running in a closed place. I mean, I sometimes even concerned about our heaters in our houses, right? So you just have to have a big enough room that's got a lot of circulation going in it. I know people in campers, when they go in campers, have to be very careful about that because you could have a carbon monoxide buildup. So I think in this case, like in the case of a camper, I might go with an electric heater because we're not having the same kind. What we're having is just an electrical resistance that's creating heat. Okay. So here we see we're going to pull those together. What happens is there's a certain metal. I will tell you the metal. We're going to watch a video right here in a second. The metal is an expensive metal. So our catalytic converters actually raise the price of our cars. Thank you, government, right? But yet, is it safer? Is it more? Are the emissions less filled with pollutants? Absolutely, they are. It works. The thing works. And I think when cars go to the dump, they pull the catalytic converter out. Because
catalytic converter off of my uncle's truck.
Seriously, when he was still like using it, I mean, it was like his own truck.
Yeah, it was in our parking
Okay,
lot.
that's because the metal that's being in there is precious metal. It's like titanium or something precious. It's expensive metal. But we'll see in a second what it's doing. We'll see right here. It's actually bringing it to that surface. Let's watch a little video on it.
In the video effects on health of air pollutants, we learned about the negative effects on our health from fuels combusted in cars. One such pollutant is nitrogen dioxide. Another is carbon monoxide. Instead of releasing these products, the catalytic converter will release harmless gases into the atmosphere. Can you recall what a catalyst does in a chemical reaction? A catalyst is a substance that causes a chemical reaction to proceed more quickly without being used up. In a catalytic converter, there are two types of catalyst at work, a reduction catalyst and an oxidation catalyst. Both types consist of a ceramic structure coated with a metal catalyst, usually platinum, rhodium and or palladium. These metals are usually formed in a honeycomb arrangement. The honeycomb structure exposes the maximum surface of catalyst to the exhaust stream, while also minimising the amount of catalyst required, as these metal catalysts are extremely expensive. The reduction catalyst is the first stage of the catalytic converter. When a nitrogen oxide or nitrogen dioxide molecule contacts the catalyst, it causes the nitrogen-oxygen bond to break, so that an O2 molecule, a harmless product, is formed along with a nitrogen molecule. All of this happens on the surface of the catalyst. Could you write an equation for this process? Pause, try it now, and check your equation when you're ready. The two balanced equations are as follows. The oxidation catalyst is the second stage of the catalytic converter. It oxidizes the unburned hydrocarbons and carbon monoxide by burning them over a platinum and palladium catalyst. The equation for this is shown here. Finally, the catalytic converter is able to monitor the level of oxygen in the exhaust stream with an oxygen sensor. This sensor is linked to an automatic control system which adjusts the carburetor in order to change the air to fuel ratio. This allows for more or less air to mix with the car's fuel before it enters the cylinders. This ensures that there is just enough oxygen in the exhaust to allow for the oxidation of unburned hydrocarbons and the carbon monoxide.
So we'll go through complete combustion, all right? So bringing in that oxygen to help with the complete combustion right there. I must have been on BBC YouTube or something. I have a bunch of British people talking today. All right, so we can see right here, we're looking now, that was our heterogeneous catalyst. We had gases going across a solid, and we're changing that. I know when they first put these out, I thought it was a catalytic converter, like a Cadillac, you know, because Cadillacs had them. No, catalyst, that's that word that comes from it. So our homogeneous catalyst, this works quite differently, y'all. It's a different thing that happens here. What goes on is we have steps, and we actually use the catalyst. Okay, so here we have our reactants. We want to get those together to make this, okay? So what our catalyst will do, it will come in and react with one of them, and when it reacts with one of them, it attracts the others to it, and then it helps connect them, and then it's released. Okay, so this we're going to see the order is going to be in our mechanism. Okay, so we're going to have a mechanical order going on right through here. All right, so let's see.
In a demonstration to show a solution catalyst, we will
real quick, just to let you know what's happening here is that there is this chemical that he's got in this beaker. That little thing spinning down there is a magnet, and this is a magnetic tray and a heating tray underneath, and it causes it to stir it. So it stirs it the whole time. So don't be distracted by that.
Heat a solution of sodium potassium tartrate. We will add a solution of hydrogen peroxide. The reaction is very slow initially, even at 60 degrees Celsius. We will then add some cobalt +2 ion. The cobalt ion forms a complex ion with the tartrate ion. The solution turns green due to the formation of this complex ion.
That's part one.
The reaction becomes very rapid. We see the evolution of carbon dioxide gas. At the end of the reaction, the solution turns back to pink, showing the regeneration of the catalyst.
Catalyst. Pretty cool, huh? Yeah. But it released all that. So it used that as the catalyst to make that reaction take place more quickly, and then the catalyst was still there. Okay, so then you might wonder, well, how do I get rid of the catalyst? I don't know how to do that. All right, so this is called the reaction mechanism. It's a series of chemical equations that tell you the step-by-step process of this homogeneous catalyst, okay, during this chemical reaction that takes place. I guess you have to write that one. All right, good. So let's take a look at it. Here we go. Let's see. We're going to take some SO2 and put oxygen in there. We're going to have it make an SO3, but that's very slow. So we're going to apparently add a catalyst to it. There it is again. And we're going to bring in, okay, so we're going to make it go faster. I don't know where I have it. Here it goes. Oh, here's our NO right here, our 2NO. We're bringing, there's our NO right there. I just ignored it. We're going to take it step 1 with our oxygen to make 2NO2. Then our 2NO2, which was made in step 1, is going to be used in step 2 to bring out our 2SO3. So NO was the catalyst. It was used in the reaction in step 1, but then recreated in step 2, so the end NO was not used up. It was certainly used. It was sort of kind of escorting, if you will, the two molecules together. Okay, you know what, y'all? I think I'm done. Hooray. So that's it. So do your study guide and be ready. We'll have some fun labs next week.